Hello, my name is Galen Bascom with the AVS lab at CU Boulder, and I'm going to talk about the dynamics analysis that we did for modeling a big space station using a point mass model for human or cargo motion aboard the spacecraft. So first, I wanted to talk a little bit about what did we aim to do and why are we trying to do it. So we had really two goals. We were looking at investigating the dynamic effects of having moving masses aboard these kind of larger structures in space. And in order to do that, goal number two, we wanted to develop the tools to kind of easily and efficiently set up these simulations to carry out these kinds of analyses. As for why now, it's just a matter of the very exciting time that we're living in, with increasingly many concepts for these kinds of big structures out in space, bigger populations of people, space habitats, big spinning structures, all kinds of exciting new ideas being developed. So we wanted to have these tools so that the effects of all these moving masses on, the overall structure could be studied. So we had a couple of modeling choices to make. So the first one was, how do you model a person? So people are pretty complex. They have lots of degrees of freedom. But for our purposes, we decided we didn't need all the details. And in fact, what we're using is just a point mass. So this could be for a person, this could be a piece of cargo, something that's moving around where we don't really care about the inertia effect so much. We're mostly just concerned about how the mass motion is affecting the spacecraft hub. So that's kind of the way I'll also refer to the space station object in space. We'll say spacecraft or hub, they're all the same thing. So for our space station, these things can be pretty complicated as well. There could be moving parts to the space station itself. We're using a single rigid body that we're modeling as a cylinder with a non-zero initial angular velocity. So totally possible to set these up in the kind of simulation framework that we use to have multiple bodies, just, more complicated. So diving a little bit into the background of the mathematical derivations, we needed to set up frames to do the dynamics derivation for the effects of these moving masses on the spacecraft. So first thing we needed was an inertial frame for taking inertial derivatives in our derivation. Then we also had this F frame attached to our moving mass. So for our purposes, that F frame isn't as important, but the dynamics derivation we did had enough generality to include moving masses that weren't just point masses, but that had kind of a fixed moment of inertia to them as well. So the F frame lets us specify, in addition to the position, velocity, acceleration of the moving mass, things like its angular velocity relative to the body as well. So for future work, when we need that capability, it's there. We also had these body fixed frames. So B is the frame, just the base body fixed frame, whatever is most natural for describing the hub motion. And then M is a sort of intermediate frame, so with a fixed position and orientation offset relative to B. For our purposes, and for many purposes, these could be kind of frames that coincide, but in some cases, the idea is that there could be some frame in which it's sort of most convenient to define the motion of the particle. As long as it's fixed to the body, we have that sort of generality in the derivation. So this RFM, that's kind of the main, most important quantity that we specify. The RFM is the position of our moving mass relative to the M point, which is the origin of the M frame. And we're also specifying the R prime FM, which is the body frame velocity and then the R double prime FM, which is the body frame acceleration. So the primes are going to be for those body frame derivatives, and then we're using dot notation for inertial derivatives. This C point is the overall system center of mass, and the BC point is the hub center of mass. Often, and in our case, this is going to be the same as B, but we're just having a little more generality. Now, in terms of the dynamics derivation, what we have for the prescribed motion is we have a known position, velocity, and acceleration relative to the body frame of our moving mass. In the full derivation, we also have that known rotational kind of position, velocity, and acceleration, but we don't really use that in this work. I'm not going to go through all of the steps of the derivation, first because I don't want to bore everybody, but secondly because it can be hard to follow if you're not really kind of carefully going through the steps. And my co-author, Leah Kenner, is doing a presentation at the Breckenridge conference where she'll be explaining kind of step by step what we did. So I encourage everyone to take a look at that as well. But the idea is that for both the translational and rotational motion on the hub, we start from very basic laws of physics, and we sort of manipulate all these quantities so that we have everything in terms that we know or can calculate. And then on kind of the left-hand side of these equations, we have either the acceleration in the kind of linear or the rotational sense of the hub, so that we can put that into our integrator. So that's true for both the translational motion, which starts from Newton's second law, or the rotational motion, which starts from sort of Euler's equations. So after doing that full dynamics derivation, the next step is putting it into software so that we have these simulation tools available. So the overall architecture that we're using is the Basilisk architecture, which is just really convenient for these spaceflight dynamics applications. So we did kind of two main pieces of development work for our purposes. The first one was developing this state effector module, which is really the dynamics saying what the effect of the moving mass is going to be on the hub, and kind of interfacing with that other module that already exists in Basilisk that takes the contributions of state effectors of this kind. We did this prescribed motion moving mass here, but there are other effectors like a hinged panel moving, or a thruster that moves, reaction wheels, all of the moving parts get kind of summed up in this spacecraft dynamics module. And the other thing that we developed was a set of profilers that feed in as messages to this dynamics module what those quantities, the RFM, R prime FM, and R double prime FM, should be at each point in time. So all of these simulation scenarios that I'm going to show you aren't really meaningful without the numbers attached. So just to go through the parameters that we used, we set up our space station as the cylinder with a specified height of 50 meters, diameter of 25 meters. This mass, we have 2 × 10⁶ kilograms, and then our inertia was just calculated based on it being a cylinder of that mass and those size parameters. We also have an initial angular velocity on the spacecraft. Then for our moving mass, we varied the mass between 200 and 2,000 kilograms, and the maximum speed between 0.5 meter per second and 5 meters per second. So walking speed, maybe about 1.2, 1.3 meters per second. So we were kind of on both sides of that. And we just picked a fixed acceleration for periods when the mass was accelerating. So the way we set up these profilers, for the linear profiler, we have kind of a constant acceleration model with a maximum velocity. So what that means is for most distances that we looked at, we would have an acceleration period, kind of a coast constant velocity period, and then a deceleration period. So that you can see in the position, we have basically the mass moving from the bottom up to the top of the cylinder. And what it looks like is sort of a parabola on both sides connected by a linear portion when the velocity is constant. So then we took a look on the effect on the space station center of mass and attitude of having this kind of linear motion from the bottom to the top. And for the plots that I'm showing here, this is kind of the most extreme case, the biggest mass with the highest speed. So you can see there's kind of a corresponding, as the mass moves up, the space station moves down, sort of as is expected. And then during the motion, you can see a change in the angular velocity of the hub. It's kind of like a rotation while the motion is happening, which leads to kind of a persistent but small attitude change due to this motion. Now, for the circular profiler that we developed, this is kind of a similar setup to the linear one, with the difference that the motion, the tangential motion is essentially linear if you were to unroll it, but we have the motion kind of curving around and staying circular. So there's this added centripetal acceleration and then the change in direction for both the velocity and the position kind of profile. So you can see the motion looks a little bit more complicated. We're walking in a complete revolution around the space station, and in the acceleration in particular, you can see these kind of discontinuities when you have that tangential acceleration turning off right here and then back on, you know, in the slow me down direction over here. So here again, we had the mass going all the way around the space station, and you can see during that motion, there are effects on the space station position. Of course, it's returning to the place it started at, so those go to 0 as we would want them to. And then it's a little hard to see in the attitude. I should have mentioned before, this is in MRP space, so those are those sigmas. But you can see pretty clearly in the angular velocity, what we have is that while that mass is moving kind of in the same direction as we had that initial angular velocity on the space station, the angular velocity of the station itself is reduced because we have, of course, conservation of the net angular momentum. There's no external torques happening here. So those were the different motions that we looked at, and we definitely want to look at more complicated cases for the motion itself. But one thing that we did do was vary the size of the mass undergoing those motions and the maximum speed that it reached. So we kept the acceleration constant, and we just looked at, okay, well, what if it could go faster? And of course, so we looked first at kind of the ending position in that linear case, and that doesn't depend at all on the speed that you're going there. Of course, the profile of how that position is going to change, the rate at which that all happens is different, but the overall position that you end up at only depends on how big of a mass you're moving kind of from one side to the other. The other thing we looked at was during the motion, what was the change in magnitude of that angular acceleration vector? And that depended on both the mass and the maximum speed. So if we look back just a few slides, basically this change that's happening right here, its magnitude is, you know, on the order of 0.01, 0.02 degrees per second. And it depends on both the size of the moving particle and how fast you're getting it to move. For the circular motion, we looked just at that change in angular velocity. Of course, you know, ending back up where you started, you could look at the position change sort of at the peak, but we didn't do that. We just looked at this change in the angular velocity, which was bigger than it was for that linear motion, which kind of makes sense again when you look at this case, which was the maximum case. You can clearly see that change in the angular velocity, and that depended in the same way on both the mass and the maximum speed. So there's a lot of further work that we want to do here, lots of different additional cases to study. We want to look at different space station sizes and geometries and see what varying those parameters does. We want to look at more complicated motion paths and, chaining maybe some of these motions together so that you have some linear, some circular motions, maybe just more complex shapes in general. And also what's happening with multiple masses, maybe Monte Carlo analyses when you have multiple masses moving on certain prescribed paths with some distribution around that. So lots more work to do, but an exciting start, and maybe the most exciting thing being the development of this dynamics module that sort of enables all of the rest of it. So thank you very much for your time and attention, and I hope you enjoyed the presentation.